Welcome back, everybody. I hope everyone had a good 3-day weekend and enjoyed their Labor Day. We'll get started today with 1.3. Yes, I know I'm not wearing my traditional garb. I wanted to wear my third tie from my son, but today is Campus Connections event at the Henderson at the Charleston campus, and I'm one of the volunteers, so I got to wear specific garb, not the fun stuff that I normally wear. So either way, we're going to talk about triangles, and then for whatever reason, they're in the same section of our text, which is dimensional analysis. One of my favorite topics, by the way, and probably one of the most useful. I think I've talked about it like on the first day, but dimensional analysis, also called unit conversions. If you're planning on taking chemistry at all, so I know some students might be in the nursing program and they're taking 120 as a math requirement. If you have to take chemistry, there's a big part of chemistry that is unit conversions, converting between grams and moles, or from centimeters cubed to liters and things like that. Those are all things that require dimensional analysis. And then I'll have a couple problems here that will help you, that are supposed to be a little bit fun. But until then, we got to talk about triangles. So once again, this might be a review for some of you, and if that's the case, awesome. But if not, I hope you enjoy. So the first thing we're going to talk about are, because it's kind of a preliminary concept, just so that we're all on the same page, are the types of angles. Let me zoom in just a smidgen. So types of angles. There are three types of angles. There is, of course, the right angle, which is exactly 90 degrees. Or if you want to study trigonometry, you might say in radians, you might say pi over 2. So taking 2 rays. And then to denote that it is truly a right angle, we do a box instead of like a little curve. We an arc of a circle. We do a little box to symbolize we are saying this is a right angle. Now, with my note-taking process, I can make a perfectly right angle, but it's kind of hard to draw by hand. It should always say that, or it might be assumed. You can always ask though on an exam, like, is that assumed to be a right angle? I will try to make sure I always put the little box to symbolize that it is 90 degrees, but in the off chance that I forget, feel free to ask for clarity. Then you have the acute angles, which are angles that are less than 90 degrees. Strictly less. So they look something along the lines of this. And so we draw a little arc to note that that's the angle. And looking at that, that looks about like maybe a 40-degree angle or something like that. So that's that one. And then, of course, the last types of angles are obtuse angles, which are angles that are greater than 90 degrees. So you have things like this. I mean, we can go in a myriad of different ways here. I mean, like, I'm not gonna, you don't need to draw this one, but like you could also just as easily draw this angle. This is an obtuse angle, that whole curve, like that whole arc. The other angle over here is an acute angle, but regardless. So those are the three types of angles, and the reason why we need to study them is because triangles are made, as I realized in my grad school, just because I'm kind of slow sometimes. It's called a triangle because it has 3 angles. Triangle. I was a TA, and I realized that during the middle of one of my TA sessions. I'm a very, very slow person sometimes. One of the things I didn't understand why they were called evergreen trees until I was about 21. It's because they're always green, evergreen. The other one, just a case in point. So when I was a kid, my dad told me a joke that said, "What's the last thing that goes through a bee's mind when it hits a windshield?" And he said, "It's butt." And I thought it was hilarious because butt. Just that's the reason why. But you know, the adults in us know that it's because it's ramming through their head when they hit the windshield. But so when I retold the joke, I said, "What's the last thing a bee thinks about before it hits a windshield?" And then I said, "It's butt." And that was the punchline. That was very funny to me, but it's not the right way to tell the joke. So I'm basically just point being is I'm very slow. My friends tried to convince me that there were different types of Mikes and Ikes. Like there were Mikes and Ikes inside the packaging. It was a big thing, and they tried to confuse me when I was when I was in college. They really went all out on that joke. So, anyways, sidetracked. Triangle classifications. So there are two subsets here. There are angle classifications, and then there's going to be side length classifications. So angle classifications. And as a small little fact that we need to write down is that the interior angles of a triangle, the three interior angles of a triangle must sum to 180 degrees. So they must always add up to exactly 180 degrees. If it adds up to more than that, it is not a triangle. And so we have number one, which is a right triangle, which is a triangle with a right angle. And so visually, that looks like just something like this. Now, granted, there's a many different ways you could draw it, but it only has one right angle. Why could it not have two right angles? From that fact up above. If it had two right angles, right, that's a 90 plus another 90 degrees. And that has to add up to 180. So your last one would have to be zero because 90 plus 90 is 180. So right triangles, you can only have one right angle. Two are the acute angles or acute triangles. And their classification, unlike a right triangle where it's just one angle needs to be a right angle, it is that it's a triangle with all acute angles. So what that typically looks like, and there's many different ones we could draw. There's infinitely many, in fact. But that is one. So all these angles are acute. Then last one of the angle classifications, as you might expect, given what we just talked about earlier, the third one will be obtuse triangles. Which is a triangle with an obtuse angle. And for the same reason with the right angle, you can only have one obtuse angle. If you had more than one, then your degree measurements would add to more than 180, making it no longer a triangle. So what this looks like typically, something along these lines. So we draw an obtuse angle and then we connect the last side. So that's the obtuse angle. And so by necessity, the other two angles of an obtuse triangle must be acute. We got 3 more, and then we can start doing some more stuff. Some actual math stuff. So we now have the side length classifications. Color. Any questions so far? Okay. So the first one is an equilateral triangle. Equilateral triangle, which is where all side lengths are equal. A triangle with all sides of equal length. So what that looks like, let's try and make it as good as I can. It looks pretty accurate. So I'm using the tick marks, the hash marks to mention that this is, those are all the same length. That's what those hash marks mean. And as a necessity of equilateral triangles, one of the cool things is that all the angles are 60 degrees. Or equilateral triangles, all angles are 60 degrees. That's kind of by virtue of how it needs to be formed. If you have them all to be like, if they all have to be equal length, then the angles that form, you can't have one be bigger than the other because then it wouldn't be able to connect. Equilateral triangle, then we have the isosceles, or if you want to actually spell it out, isosceles, isosceles triangle, because I can never remember how to spell it offhand. I have to say isosceles. And that's at least 2 sides of equal length. I should have said a triangle with at least 2 sides of equal length, but I'm not going to change it now. So there are many different ones we could draw, but we're going to draw it like this. So these 2 sides are the same length here, and then this one's different. We'll call this one the base, and then these 2 the legs. Now that is an obtuse isosceles triangle, but you can also have acute isosceles triangles or isosceles right triangles. There's like these classifications, much like with quadrilaterals, there's overlap between certain things. All right. And the last one is the scalene triangle, which is a triangle where a triangle with all sides of different length. So something like this. So we'll say this one is one measurement, this is another measurement, and this is another measurement. All the different side lengths. And just like with the isosceles and with the the equilateral is kind of a unique case. But with scalene triangles, you can have a right scalene triangle, you can have an obtuse scalene triangle, you can have an acute scalene triangle. So that's what we're going to do first is like classifying them. Super excited. I know. It's a lot of fun, not much math going on, but there are some fun things to go on soon enough. I just can't wait. Honestly, I just can't wait for unit conversions, but I don't think we're gonna get that until next week because we've got to talk about similar triangles and a couple other things. So, as a small example, unless there's any questions on these classifications. So now you guys are the proud owners of the ability to be that person at parties and like that's a triangle. Well, actually, that's an equilateral triangle. Actually, that's a scalene triangle. And then you can be like a Starbucks barista who has to correct people all the time. Want a large caramel macchiato. Oh, you mean a venti caramel macchiato? They had you do that. Fun fact. I'm in a Starbucks training manual. Fun fact. True story. I used to work at the Alki Starbucks in near Alki Beach in Washington. It's a very, very pretty Starbucks. And for whatever reason, they chose our store to do some promotional shoots. And so there's a picture of me and how to address customers at the POS station. And I'm just talking to a customer going, ha ha. And then I land zoom in on my hand writing on the cup. I don't know if they still have it, but at least I was in there for a while. So now you have the ability to be a Starbucks barista for them now that you know these different classifications. So classify the following triangles. So part A, and we're just going to do them right above. So it's going to be this type of a triangle. And it's going to say 6 feet, 6 feet, and then the bottom is 4 feet. Terrible handwriting. Part B will be this. And of course, these are not drawn to scale, by the way. Don't judge me. 10 inches, 8 inches, and 6 inches. And then part C will be this one. 10 centimeters, 4 centimeters, and 5 centimeters. Every triangle can fit into one of the 3 categories in each situation. It'll have an angle classification and it will have a side length classification. I'll let you draw those and then we'll go ahead and go through them. Oh, and for the B, it should have a little box there. Otherwise, there would be no and we'll talk about that one in a second. I'm pretty sure on the homeworks, on an exam, I would definitely make sure to have that right angle symbol mentioned. But I'm pretty sure on your homeworks as well that it is always mentioned unless it does not matter. So the first one, none of those angles look to be larger than or equal to 90 degrees. So they're all less than 90 degrees. So this one is acute. And because it has 2 side lengths that are the same length, then it is isosceles. So acute and isosceles. So yes, if this symbol was not there, there is no way to know if that's actually a right angle. It's pretty obvious, it's pretty clear when we look at it that it should be right, but we can't be certain because maybe it's just one of those ones where it's just a hair. You busted out your own protractor. Do you guys remember protractors? You guys still have one? You should. It's very important. You're going to need it all the time in your adult life. True story. I have one in my pocket. No, I'm kidding. But it could be one of those ones that's like 90.1 degrees. So we don't necessarily know. That's why it should have this. And if it doesn't, please let me know so I can update the homework and fix that graphic. So because it has a right angle there, we know immediately that this is a right triangle. And then looking at the side lengths, all the side lengths are of different measures. So it's a right triangle, and it is also scalene. And the last one, it has an angle that is larger than 90 degrees. The one that is formed from the 5 centimeter and the 4 centimeter side lengths. So it is an obtuse triangle. I don't know why it's being so difficult. And it is also scalene because all these side lengths are of different length. So that's how we classify them. But then one of the more important things is trying to figure out, like one of the more important things that we're concerned about in this course is area and perimeter of these shapes. Because that's like one of the most useful applications of shapes is understanding their areas and their perimeters for things like trying to figure out how many feet of baseboard you need for, like, if you're trying to remodel your house or something like that, how much how many feet of baseboard do you need? You'll use the perimeter. Or how much carpet do you need? And like maybe you have a triangular room. I don't know. Maybe you do. Be weird, but I don't know what you would really put in a corner of a triangular room, but could still happen. So on to bigger and more fun things, more mathy things, perimeter and area. So we're going to be given a generic triangle that we're going to draw like that. And we'll call the bottom, this measurement we'll call B for the base. And we'll call these side lengths A and C, though it doesn't really matter. Like, actually, let's avoid that. It's not necessary. Sorry. Changing my mind. And then we'll call this the height of the triangle. So the perimeter formula, just like we've been talking about with quadrilaterals, perimeter, there are formulas that you can calculate that you can write down for any shape, but I really don't think that's necessary because perimeter is always the same. It is just adding up all the side lengths. So perimeter, just like before, sum of all 3 sides, not H. So remember, H is not a side length. That's what I've drawn. That's why I've drawn it in dash as a dashed line. H is a measurement, but is not a side length. So it does not add to the perimeter. And one thing to note about this, by the way, is that the base is always perpendicular to the height. So I should probably draw a little right angle there. That is always the height. Height of the triangle is always perpendicular to the base when you're using these formulas. So we're going to be using a formula in just a moment to figure out the area. Now, there, like, one thing I will note, by the way, is this is how I've oriented it, but just for the sake of an argument, so I've got roughly the same one here. You could have just as easily made this the height. And then this the base. It doesn't matter because all I need to do is just kind of reorient it to view it in the right light. I know the B is upside down now, but so just so we're clear, it doesn't matter how you decide to do it. The height always needs to be perpendicular to whatever you're going to call your base. So back to the point, the area formula. The area of a triangle is equal to 1/2 the base times the height. Or more preferably 1/2 b times h. That's the way we usually write it so that we don't have to write out long words. Now, every once in a while, I'll throw out proofs just because this one's a really, really cute proof. Why would it be 1/2 the base times the height? Have you ever wondered that fact? Maybe you have, maybe you have not. Maybe maybe your teacher just said, just do it, and they hit you over the head like mine did. Maybe that's what they did. But if not, maybe they showed you. So the reason for it is, imagine you take that triangle, right? And then let's just say, for the sake of an argument, I just took that same triangle and I just kind of flopped it up above. That's the exact same triangle, just in a different orientation. And so this distance is, once again, and you don't need to draw this, by the way, I should have specified. This is just for proof's sake. That's the height. And then once again, this is the base. And what type of shape is that? That is a parallelogram. And the area of a parallelogram is base times height. So the area of the whole shape would be base times height, but we only want one of the triangles. So we'll divide the total number by 2. Boom, proof. So pretty cool. I'm expecting an ooh or an ah. There we go. I hear it in your guys' thoughts. I know it's fascinating, but you don't want to appear like you're catering to the teacher. So I get you. I get you. Okay. So let's get some examples of calculating those things. Find the area and perimeter. Of part A will be a triangle like this. The quintessential triangle picture, and it'll say the measurements are 11 feet, 5 feet, and 8 feet for the side lengths. And then it gives us this measurement and says that that is 4 feet. And then part B will be a right triangle like this. And so the measurements are 13 centimeters, 12 centimeters, and 5 centimeters. That's clearly a 4. I'm kidding, of course. I just get to be snarky for a second. That's clear. Like I meant to write a 4. That's a pretty bad 4. Thank you for calling me out. I appreciate it. Every once in a while, my handwriting sucks. So, all right. I'll let you draw them first, and then we'll get started. I think we might just get to dimension analysis, which would be really exciting. I love dimensional analysis. I've used dimensional analysis. Like, I know some of these things don't seem like they're very, very useful in daily life, but dimensional analysis really will enrich your life. It will make you a more fun person. True story. So solution. Once you see the examples I got, I'm just so excited. I'm sorry, guys. I love dimensional analysis. I'm so bummed that it's only like it's in the first 2 weeks of class that we get to talk about it. So we don't get to build up for it. But anyways, part A. I'm not going to redraw the picture. I mean, you can if you want to, but perimeter, very quick. Perimeter, just add up all the side lengths, not the purple one, because that is, of course, the height. So perimeter will equal 8 plus 5 plus 11, which will be, and you can use your calculator. What did you say? 24? That looks right to me. Yes, 24, but don't forget your units, 24 feet. And just as a reminder, once again, perimeter is a one-dimensional idea. It's how long it would take for me to walk around the object. Whereas area is a two-dimensional thing. You need 2 dimensions to draw area. So area here, 1/2 the base times the height. If you're trying to memorize the formula, it always helps to rewrite the formula every single time you use it. But area is equal to 1/2 the base times the height, which in this case is 1/2 the base, which is 11 in this case, because that is the side length that is perpendicular to our purple measurement of height, times the height, which is 4. And if you do that, you should get 22 feet squared. Or feet, if you really want to be weird. Any questions on that? Not too terrible. B, though, I deliberately chose B to be a right triangle for one specific reason. So perimeter, no sweat, right? Add up all the side lengths, we're good, we're golden. So perimeter is going to equal, doesn't matter which one you put first, I'm just going to start with the vertical side length. So 5 plus 13 plus 12. That's 25 plus 5, that's 30. Yes, 30 centimeters. Now for area, the area, once again, the formula, area is 1/2 the base times the height. But you might be thinking, whoa, Phil, I don't have a base. I don't have a height. I only have a base. The 5 is the height. So in the situation where you have a right triangle, one of the legs ends up being the height. So I'm going to do it kind of a comment here and say that the side length is also the height. Because it's perpendicular to the base. So in order for, once again, in order for it to be a height measurement, it needs to be perpendicular to one of the side lengths. In this case, it's perpendicular to the 12 centimeter side length, making it the height when you look at it that way. And right triangles are the only ones that do that, where one of their side lengths ends up being the height of the triangle as well. So 1/2 the base. Times the height, which is 5, which will be, once again, 30, strangely enough, 30 centimeters squared. Now that can happen. It can be that the both of them, like they're not the same number because of the unit measurements. One of them is 30 centimeters, where one of them is 30 centimeters squared. But it can happen that they give you the same measurement. It could be that your perimeter is larger than your area. It could be that your area is larger than your perimeter. It all depends on the problem. So that's not a good, like, just because your area is smaller doesn't necessarily mean you did it wrong. Or that they were equal, it doesn't mean you did it wrong. Any questions on that? Okay. So that's how we find area and perimeter. So we can use that in different situations. But now, one of the other ones that what we want to talk about are what's called similar triangles. But in order to talk about similar triangles, we need to talk about proportions really quick. So a little tiny review on proportions. So now there are things that we call proportional relationships and things like that. And you've probably heard that terminology outside of mathematics, but if you haven't, in terms of mathematics, a proportion I'm going to kind of underline that with a squiggly line to say that it's kind of like a definition, just not a definition that we necessarily need. A proportion is an equation where two ratios are set equal to each other. Now, there are simple proportional relationships, and then there are ones where you're actually going to like where it's just a true statement. And then there are ones that are actually things where you're going to solve them. So the most simple case of a proportion would be something like 2/3 equals 6/9. That is a purely mathematical proportion. There's no context behind it at all. Like it's not trying to figure out the ratio between like you're trying to like triple a recipe or whatever for like, and you need a specific ratio between cups of flour and number of eggs or something like that. It's not in a real life context. It's just a purely mathematical true statement. 2/3, if you plug that into a calculator, you'll get 0.6 repeating. And if you plug in 6/9 into your calculator, you'll also get 0.6 repeating. So one way to visualize that is to draw a little box of why this is true. So I'll draw a box, which I will divide into 3 equal portions. And then I will fill in the first 2. Why won't you let me? No. There we go. So that is 2/3, 2/3 of a whole, right? And then if I were to draw the same whole, but instead of dividing it into 3 pieces, I divide it into 9 pieces. So I'll do 2 vertical lines and 2 horizontal lines. I've divided the whole into exactly 9 pieces instead of 3 pieces, and 6/9, well, 1, 2, 3, 4, 5, 6, it gives me the exact same thing. Well, that was a rectangle. And it ends up being the exact same amount. So that is a what we call a simple proportional relationship, in that it is not, there's no context behind it. There's nothing to do. It's just a true statement. If we have time, like I'm looking at the 2/3 and realizing there's a fun little tidbit. Don't write this down, but this is just something if we have time at the end of class. Did you guys know that 0.9 repeating is equal to 1? It's a true story. 0.9 repeating is actually equal to 1. It's not smaller than it. It's not like basically it. It is exactly 1. And I'll show you some proofs later on if we have time. And if we don't have time, then you can definitely come to my office hours and I'll show you why it's true. But the reason why I want to study proportional proportions is to how to solve a proportional relationship. So, example, solve the following. This is a proportional equation. Like, in essence, it is a linear equation, but because it's going to be a fraction equals a fraction, we call them proportional equations. So part A will be 4/12 is equal to x over 9. And part B will be x/20 equals 6/15. That's the small dot there. That wasn't supposed to be there. Let's get rid of that. There we go. Now, how you solve this is your own prerogative. Just as long as it's mathematically valid, I could not care less. The traditional way that we solve these is with a method called cross multiplication. If you've heard it before, awesome. If you haven't, I'll show you. So solution. Part A, we have 4 over 12 equals x over 9. The long-winded way of doing it is to find a common denominator between 12 and 9 and multiply across. So common denominator of 12 and 9 would be 9 times 4, 36. 36. So you can multiply both sides by 36 to cancel all the fractions, but the nicer way, the quicker way to do it is to just what we do is we go cross multiplication. So we multiply the denominator of the first fraction by the numerator of the second fraction, and then vice versa. So this becomes 12 times x. So 12x is equal to 4 times 9, which gives us 12x is equal to 36. And I realize that this is the first time we've really had to solve an equation in this class. So in case you don't know, to solve an equation, you are trying to find the value of x that makes a true statement. And a true statement is something like 5 equals 5, or 0 equals 0, or negative 10 equals negative 10. Any of those things, like as long as it makes a true statement, you have found a solution. So how you do it is you try to get the x by itself. And you want to work outside to inside. So get rid of the farthest things away first, and then work your way inside until you get the x all by itself. And to get rid of an operation, you have to do the opposite of the operation. So this 12 is attached to the x. It's 12 times x. So to undo the multiplication, I will divide by 12. So I'm going to divide both sides by 12, and that will cancel it on the left, leaving me with just the x. X is equal to 3. And that is our solution. And the one thing I love about equations, is one of my favorite parts about mathematics, is that with equations, almost always, now there's a few hiccups every once in a while, but that's for a later math course. But you can always check your work to make sure you have made a true statement. So if I plug in 3 into the original equation, I'm not going to plug it into anything later than the original equation. And the reason for that is if I try and plug it in here or here, I'm checking my work in work that I've already messed with. So, and that's where human error can occur, right? I could have accidentally saw this as a like maybe it was instead 40 and I just forgot to write the 0. In which case it will solve this version, but it won't actually solve the original version. So there's a reason to check it in the original version of your equation, not the later stuff. And so if I plug in 3 into both of these equations, I guarantee you will get 0.3 repeating. Both sides, if I plug in 3, so just as a checking tool, if you ever want to check, you don't have to write this down, but 4 12ths, does that equal 3 over 9? 4 12ths, if you plug it into your calculator, you'll see that it equals 1/3 or 0.3 repeating. And does that equal 1/3? Yes, it does. So we know we did it right. So one of my favorite things about equations is you can always check your answer. You can always verify that you got the right thing. Any questions on that? Yes. Mm-hmm.
It's not a question.
Oh, yeah.
But on the 12x equals 4.9, you can just simplify 12 or 2. You don't have to get the big number.
Oh, the 4 and the 12?
Yeah.
Yeah, you could simplify that. Absolutely. So, sorry, what's the name? Yozen? Yozen was asking, could you simplify this thing first? And the answer is absolutely. 4 over 12, there's a common factor of 4, because 12 is the same thing as 4 times 3. So you could really just write this as 1/3. So instead, you could write 1/3 is equal to x over 9, and then you're dealing with smaller numbers. At the end of the day, we'll give you the exact same answer, but it saves you a little bit of, it allows you to do it easier in your head with the mental math. So totally fine to do so. Let's see here. Anything else I want to mention? Why did one reason as to what's going on here? Why does cross multiplication work? Because one of the things I love about mathematics is there's always a reason why something works. You should always be questioning what you're learning. I could be, for all you know, I could be a fraud up here. I could have kidnapped the real Phil and hide him in my basement, and I'm just teaching you bogus math. You don't know. So how do you know that it's really me and I'm actually a math teacher? Well, there's a reason why it works. The reason why we can do this, why we can just magically multiply these two numbers together and these two numbers together. It all stems from this fact. So 4 over 12 equals x over 9. You don't have to write this down. But one of the things that we know about math, like, and the reason why I really want to spend a little moment on this is that equations are a very, very important thing, and they have big rules about them. One of the rules is that you can multiply both sides of an equation by any number, any non-zero number, and it remains true. So you can double both sides, you can half both sides, you can quadruple both sides, and everything always remains the same. So the reason why I can do this magic trick is that if I multiply both sides by 9, that cancels the 9 on the right. And 9 is really the same thing as 9 over 1. And when you multiply two fractions together, you multiply their numerators and you multiply their denominators. So this becomes 9 times 4 over 12, or I should go back to black for a second. It becomes 9 times 4 over 12 is equal to x. Technically over 1, if we really want to be particular. And then what I can do, so this is the same equation. I have not done anything that has been mathematically invalid. And then the next thing that I'm doing is I'm multiplying both sides by 12. That cancels the 12 on the left-hand side, giving me on the left-hand side exactly 9 times 4, and on the right side 12 times x, or 12x. That is why cross multiplication works. It's basically doing two steps in one. It's multiplying by one of the, it's multiplying by 9 first and then by 12 first to both sides of the equation. That's what's happening. That's why cross multiplication works. But key thing to understand, cross multiplication only works if you have a fraction equals a fraction. So as long as it is just using some, if I have a over b equals c over d, right? Or box over triangle equals circle over square, then I can use cross multiplication. Where I cannot use cross multiplication, and I'm bringing this up because I've seen it happen time and time again for students, is if I have 4/12 equals x over 9 plus 1. In this situation, I cannot do cross multiplication because it is not a fraction equals a fraction. Cross multiplication only works if you have a fraction equaling a fraction. Now, will we see this very often in this course? Probably not. But if you see me in the street and I have this problem, just shove it in your face and say, solve it. You'll know not to use cross multiplication now. Okay. I'd like you guys to solve part B if you haven't already done so. I will slowly fill in details. And Yosin, right? And Yosin suggested you can also simplify 6 over 15. You could reduce it. There's a common factor of 3 that can be canceled out, but it's not necessary. And if you want to skip some arithmetic, by the way, please be my guest. If you feel comfortable skipping arithmetic, oh, I don't think I've asked. I've put this here. I don't think I've mentioned this in this class. One of the things that students love to ask is, well, how much work do I need to show on my exams? How much work do I need to show? And my answer to you is, imagine you were explaining this problem to another classmate who has the same, like basically, imagine you were explaining it to yourself. A person who has the exact same like level of understanding of the course as you do. You should, like, that person should be able to look at your work and see how everything came to be. So if you're missing a bunch of stuff that a person who had the same level of understanding as you did, or maybe a little less than you did, they should be able to look at your work and see how you got it. Okay, that's my golden rule. So you should get either x equals 8 or 8 equals x, but they're the same thing. There's a same thing we say about equal signs is that they are a reflexive relationship. If I say like a equals b is the same thing as saying b equals a. You can flip the two terms and it still remains true. So 8 equals x is correct. Most people would prefer seeing the variable first. That's just the convention, is that you should say the variable equals the number or whatever. But this is completely fine to leave and box in on an exam. You can just write 8 equals x and call it good. Any questions on that? So once again, I cross multiplied and I did this step, but you could immediately go from here to here. 20 times 6 is 120. X times 15 is 15x. So if you want to skip that middle step, please be my guest. Any questions on that? All right. The whole point of studying proportional relationships is that this allows us to talk about similar triangles. The definition: similar triangles are triangles, of course, with same angle measurements but different side lengths. Same angle measurements, just one is bigger than the other or one is smaller than the other. It's just like if you took like an image that you've copy and pasted onto a Word document, you can make it larger or make it smaller. Those things have the exact same angles. It's just one is bigger than the other. And so, as an example of this, one of the ones that they love to throw at you like on like SATs and things like that is inscribed similar triangles, and I'll show you what that is. So we're going to draw a large triangle right here. And then I will draw a line that is parallel to the base. So in fact, so there are actually two triangles in here. There's this triangle. Come on, that's a straight line. And then there is the triangle at large. There, change that to purple. Wait. Phil, is this absolutely necessary? Yes. Well, actually. So you can split this up into two different triangles. There's the orange one. I know it's not drawn to scale. It'll drive me nuts. And then here's the cool thing. Wait, no, I want to duplicate. I wanted to change to purple. And those are similar triangles. So what happens is you can look at this as two triangles, one inside of the other. And so why do we care about similar triangles? What's the big deal? Yeah, they're the same triangle, like the same triangle, just one's bigger than the other. What's the big deal? Well, there's a nice little factoid that says that similar triangles have corresponding angles that are equal in measure and corresponding sides that are equal in proportion. I'm going to underline that last statement. Corresponding sides are equal in proportion. That's going to be the important thing to us. They are equal in proportion, so you can form proportional relationships. Let's see that in action. Shit, that's flat. Otherwise, it's going to drive me nuts. Now you might be thinking to yourself, Phil, I don't need to color, like I could do this in my sleep. This is totes easy, as the kids say. This is just this is child's play. But if they're in weird orientations, it can be a little bit hard to figure out which side goes with which side. So a little tip: color code your triangles. So I'm going to draw two similar triangles, and I'll show you what I mean. That's slightly better. That's making it look worse. All right, and then what I'm going to do is I'm going to duplicate this, make this one larger, and I'm going to change its orientation like that. So let's say you're given this problem on a homework or a quiz or an exam, and it's telling you to find the missing side lengths. Because they're in different orientations, it can be hard to identify which one goes where. And so what I like to do is I like to color code. So highlighter, but you can use I'm going to use a highlighter, but you can use a colored pen or pencil. And you don't even need to have colored pens or pencils. You can also do it. One thing that I've seen students do if they don't want to do it is they make this one into hash marks, and then this one into squigglies, and then this one into loops, like that. That's a way to color code without actually having colors. But since I do have colors available, I will do it. So let's go ahead and say, I usually start with the biggest side length, and I'm going to color code that with the other biggest side length. And then I look for the smallest side length, because those are the two easier ones to find, is the biggest one and the smallest one. The middle side length, that one's kind of the harder one to find. And so we'll color code the smallest one. And that's the smallest one here. And then last but not least, the other side length. That. Very, very useful just to make sure that you don't mess up your proportional relationships. So with that, I'm going to show you all the proportions you can set up. So all of their side lengths are equal in proportion. So depending on how you want to do it, there are, let's see here, 1, 2, 3, 4, 6. There's a lot of different proportional equations you can set up. The most common ones is saying things like big green over small green is equal to big red over small red is equal to big blue over small blue. But there's many different ways you can do this. Those are the ones that are like most common used. And less common, you could do things like small green over small blue equals big green over big blue. And I guarantee you, if you do that, you will get the exact same answer. You will be able to solve them in however you want, and so on and so forth, et cetera, et cetera. And then that equals big red over, or wait, no, never mind. And there's a bunch of different ones. You could also do small red over small blue will be equal to big red over big blue, and so on and so forth. So there's many different equations you can solve for them, but the most common ones are these bad boys or girls or them, however you want to say it. These guys are the most common. So let's use them in a problem to set it up. And then I think we'll have time to do an example of why this would be super useful. Super useful, like you'll see this in your daily life all the time. So example, we're gonna do a purely math example first. So given similar triangles, find DE and DF. So in case you haven't seen this geometric notation, if I write two letters and a line above it, I'm talking about a line segment connecting 2 points that we've labeled D and E, which you'll see in just a moment. So the first triangle will be the slightly bigger one. Which is A in the top, B in the bottom left, and C in the bottom right. Then I'm going to take this and duplicate and make a smaller one. That. I call this one top one is D, bottom one is E, and bottom left and bottom right is F. And so it gives us all of ABC, the triangle ABC. The AB's measurement is 17 feet. AC is 15 feet. And BC is 11 feet. I know it's not to scale. Please forgive me. And then DE is unknown. DF is unknown, but EF is 8 feet. So I'll let you draw that. I know that takes a little bit of time, so I'll let you draw that, and then I will onward. Here we got 15 minutes. Perfect. All right. So I'm going to color code it. And I'm also going to label my unknown sides. So, I mean, we could keep it labeled as DE and DF line segments, but it's better to label them with letters, with variables. Let's call it X and Y, but it doesn't matter which one you choose. I'm going to call DEX and DFY. Let's use not blue. Let's use orange. X and Y. So I'm going to color code it. And luckily for us in this problem, both similar triangles are in the same orientation. So there's no we can just do it without even having to worry about it. like color coding it, but I'm still going to choose it just as as if it wasn't the case that it was a nice orange. Yes. Yes, exactly right. Yes. So because they are unknown, I'm just going to call them X and Y, but you could also use A and B, or like, if you really wanted to, and I would encourage this. I've never seen a student do it, but you could make this one a kitty cat. And you can make this one a doggy. I've actually seen that happen you could definitely do that. True story. A variable is just an unknown quantity that we've represented with a symbol. So feel free to let your inner Bob Ross get channeled here. You can use whatever your letters. It's just mathematicians were very boring. We decided to just use X and Y. I had a question back here.
The number for the first triangle, there's 17, 11, and then what's the other number?
15. Actually, a famous like a famous little funny math exam is a person did a problem in differential equations where he defined all his variables using a story with a squirrel and acorns and a dog, and it works out if you follow it, if you follow it and just assume that those are actual variables, it works out. And the teacher wrote, please don't do this ever again, because it was very, very hard to chase when you're using things that aren't well known. But anyways, these are the two side lengths that are similar. Then we'll do the other ones right here. And because they're in the same orientation, we don't need to worry about it. But like that. So we need to find what X and what Y are. So we can do it in however we want. We can do just based on this fact right here. We can work we want to know what X is, right? And we want to know what Y is. So we can do small blue divided by big blue. But you could also do big blue divided by small blue. It's the same thing. As long as it's consistent, which if the numerator is small in the first one, the numerator should be small in the second one. And so on and so forth. So small blue over big blue is equal to, should I do small red over big red, or should I do small green over big green? Small red. If I did small green, then I get X, so let's just assume that would be the case. If I did this, so don't write this down. I'm going to write this in red actually to say that this is not what we want to do. If I did small green over big green, then I would get X over 17, small blue over big blue, is equal to small green, Y over big green, which is 15. And unfortunately, that's a two-variable equation. And so there's no way to solve for one of the variables. This is something you'll learn if you decide to take later math courses. There are ways to find solutions to this, but that's not something we're really privy to right now. So this won't work for us because now we have two variables in our equation, which makes it hard to do. So instead, we will do small red over big red. Small red was 8 divided by 11. At which point, this is a proportional equation. We can cross multiply to solve it. And that's what we'll do. Cross multiply. You get 11x is equal to 8 times 17, which is 80 plus 56. That's 136. Yeah. And we want to get x by itself. We don't want to have 11x equals. We want to have x equals. So because the 11 is being multiplied into the x, to undo that multiplication, we will divide by 11 and get that x is equal to leaving it as 136 over 11 would be fine. But if we want an approximation, we'll write out the full decimal expansion that we see, 12.363636 on and on forever. And let's just say we want to approximate to the nearest tenth, which on my exam, I would write approximate to the nearest tenth or first decimal spot. So looking at the first decimal, it is a 3 looking to the number to the right of it. It is 6, which is larger than or equal to 5. So we will round up to get that this is approximately 12.4. Don't forget your units, 12 feet. 12.4 feet. I encourage you, if you want to like just have a fun time this weekend with your buds, verify that if you do big blue over small blue equals big red over small red, you will get the exact same answer. But like no matter how you set it up, as long as you're consistent in how you set it up, you should get the exact same answer. So that's pretty cool. I mean, cool, I guess. It's an abusive notation. And then the next one. So now that I know what X is, now that I know the small blue, to solve for the green, to solve for Y, small green, so 4X, I should have said, for Y, small green divided by big green is equal to. Now I could set it up, now that I know what X is, I could set it up as small red over big red, small blue over big blue. However, I'm not going to do that. And the reason for that, the reason why I'm not going to do that is that I've written an approximation for X. Now, our homework, like on an exam, I give you full credit because you're doing exactly what you need to do. But with Canvas, it can be pretty particular about the exact value, where and it doesn't have my brain to see, oh, I see what you did. You just used the blue side lengths now that you found X. But because our X value is an approximation, it won't give us the exact answer. We'll probably be off by maybe 100th or 300ths of a number. So that's why we should still stick with small red over big red. That is to say small green, which is Y, over big green, which is 15, is equal to small red, which is 8, over big red, which is 11. Cross multiply. 11Y is equal to 80 plus 40, which is 120. Divide both sides by 11 to get the Y by itself, because it's 11 times Y. So to undo that multiplication, we'll do division, because those are inverse operations. And Y will equal, if you plug it into your calculator, you get 10.909090, on and on forever. So approximately, if we're rounding to the nearest tenth, we're looking at the first decimal spot. The number to the right is 0, so we will round down because it's less than 5 and just get 10.9 feet. Any questions on that? All right. So I'm going to add in an extra problem. Like we probably will finish it today, but if we don't, no big deal. It'll be a fun problem to do with the boys over the weekend. Just get your friends rallied together and do it. It'd be excellent. Your Discord channel or whatever you want to do, post this there. I don't know how kids talk these days. Do you guys use Discord? Is that what we do? I don't know. Anyways, so word problem. You're worried a tree might fall on your house. How it's oriented, you can't like the shadows from the sun never actually end up casting a shadow where you could tell whether or not it was going to hit your house. So you don't know. right? Like if you had the sun, it was giving you a good shadow, then like if it ended up being on your house, then you know that it would hit it. But you're worried that it might fall on your house. At noon, you notice the tree casts a, let's say, a 20-foot shadow. How amazing. It has an exact 20-foot shadow. It's very common in real life that they're exactly 20 feet. True story. Every tree, if you ever measured them, they're always 20 feet. But cast 20-foot shadow, and you standing at 6.1 feet tall cast a let's say a 5-foot shadow. Also amazing. Wonderful that it actually ends up being perfect 5-foot shadow. If the tree is, let's say, 16 feet away from your house, will it hit if it falls? And you might be thinking to yourself, well, Phil, I'll just cut it and make sure that it falls in a different direction, right? Well, what if you have a bunch of walls around and then it would fall in the walls and ruin your walls, and then you have to hire a masoner to fix them. HOA is going to be on your ass, you know. You want to cut this so conveniently that it'll fall into your yard and you don't have to worry about ruining your neighbor's wall, like the wall that you and your neighbor share. So you could actually use similar triangles to figure this out. So let's figure out how tall the tree is. That's what we need to do first. If we figure out how tall it is, then we can figure out how far, like how long it will, like once it cracks and falls, how far it will go into our yard and whether or not it'll be more than 16 feet. Because you can't sit up, like you have tape measures, that's how you measure the 20 feet, but you can't, like tape measure won't go all the way up to 20 feet. It's just like to measure the height of the tree, it's impossible. It'd be too wobbly. So let's draw a little picture to get ourselves visualizing this. So we have our super accurate tree, and it's casting a shadow to here. And this distance is 20 feet. And this is unknown. We'll call it, we'll do a question mark. And then here you are standing at 6.1 feet, and you're casting a 5-foot shadow. Now, one thing that is assumed that we know, but like you wouldn't know this unless I explain it to you right now. When the sun, like relatively speaking, I mean, there's probably a small margin of error, but as long as you're sitting next to the tree, the sun is casting the exact same type of shadow. So these end up being similar triangles. These are similar triangles. And we are out of time, but this will be a good problem. You will now be able to, if you want to do this weekend, crack open a cold one, which I assume means Mountain Dew. That's what kids say, right? When they say crack open a cold one, they mean a good old Mountain Dew Baja Blast or something like that. So go ahead and do that with your friends. I'm sure this is a great bonding experience. Your homework for this week is just 1.2. So if you haven't already finished that, since we finished 1.2 last week, if you haven't already finished it, please do so. 1.3 is not due this week, it's due next week, but you can at least get a lot, well, no, because so hold off on 1.3 homework for now because you have to be able to do all of 1.3 in order to do it. So anyways, that'll be it for today. If you have any questions, feel free to email me. Otherwise, you guys have a great rest of your week and a great weekend, and I'll see you on Monday. We actually have school on Monday this time. Oh, actually, wait, no, never mind.